For thousands, today we know that the Earth is a mere speck in space. In trying to learn about the universe in which he lived, man has always been far too ready to believe his own eyes. He found it extremely difficult to shake off his terrestrial perspectives when looking out at the vast distances and tremendous intervals of time that prevail in the universe. In this series of programs, we are going to try to tell you something about the wonder and mystery of space, about some of the strange and often magnificent objects that are out there in space, and something about the relationship of our Earth to these objects, for our Earth is itself a very tiny ball in space. We live on an Earth which is a planet, a member of the solar system, a system which consists of 9 planets revolving about a central star that we call the Sun. Here, in this little arrangement, we can see the 9 planets. There are 9 planets. There are 31 satellites which belong to several of these planets. And there are an unknown number of minor planets, the asteroids, and an unknown but still larger number of comets and meteors which thread their way in among these planets. Now, of course, this just shows the planets. It doesn't show these minor objects. And there is no attempt made in this little affair to give you any conception of a size or distance scale. You can't make a scale model of anything astronomical. Here, for instance, in this model is the Earth. And if this were to scale, the Sun here would have to be at least 110 times the size of the Earth, about so big. And as far as distance is concerned, the Earth couldn't even be in the room. Now, let's talk about these distances for a moment. Suppose we were to take the distances in the solar system and divide them by 1,000,000, and then take that reduced solar system, reduced to a scale of 1 in 1,000,000, and lay it over the United States. We'll put the Sun at New York. Then Mercury, the nearest planet to the Sun, would travel over a pleasant little suburban town in New Jersey, Morristown, 36 miles from New York, Mercury 36 million miles from the Sun. On that same scale, Venus would come over Camden, New Jersey. The Earth would be in the western suburbs of Philadelphia. Mars would be at about where Harrisburg is, and these minor planets, the asteroids, would travel in a path lying generally between Harrisburg and Pittsburgh. Jupiter would be outside of Pennsylvania for the first time. It would lie over Detroit. Saturn would be over St. Louis, Missouri. Uranus over El Paso, Texas. Neptune would be completely out of the United States, lying some 100 or so miles west of San Francisco in the Pacific Ocean, while Pluto, the most distant planet of the solar system, would be really out in the Pacific, at least 1,000 miles beyond Neptune. Now, remember, this is to scale. These distances are all divided by 1,000,000, and this is the relationship of it. Remember, too, that unlike the conditions in the United States where we have farms and cities and towns and villages and so on scattered all through that, there is really nothing out in space between the planets. To all intents and purposes, space is virtually empty. Now, this whole system is really rather flat. If we were to put it into a sort of a super hat box, 3 feet in diameter, that hat box need only be about 8 inches deep. Distances in the solar system are tremendous. There is only one object permanently in the system within 1,000,000 miles of the Earth, and that is our moon. The next nearest object, occasionally, is Venus, which can be within 26 million miles of the Earth. Now, as long as we stay in the solar system, we're going to be able to use miles as our unit of measurement. When we get outside of the system, we're going to have to find another means of measuring distance. Distances in astronomy are really overwhelming. Now, man's conception of the universe is based upon what he saw. He lived upon a tremendous Earth, obviously the biggest thing in space. Around it went a bright sun, probably made of very hot rock and about as big as a man's head, and a pale moon, less hot but about the same size. Then there were 5 strange, wandering stars that moved at varying speeds among the other stars, which were fixed to a sort of hollow shell inside of which was everything else. These wandering stars were the planets. The whole business moved about the Earth and was placed there solely for man's entertainment and admiration. As man grew up scientifically, he had to give up this rather grandiose conception of the Earth. But it's only been within the last 500 years that man has come to realize that the Earth was not the center of the universe or even the center of the solar system. That the Earth was just one of 9 planets that moved about the sun in orderly progression. And threaded in among these planets were these other small objects that we spoke of, the asteroids, the comets, and the meteors. Now here is a diagram of the solar system showing the objects in their proper order. Here's the sun, of course, in what we might call the middle, the focus of the whole thing. Now, as we go out from the sun, we meet the planets in this order. First Mercury, then Venus, then the Earth, and then Mars. And now even in this diagram, we've got to change our scale a little bit. Here, down below, is the inner circle, you see, with Mars as the outermost planet. Then, outside of Mars, come Jupiter, Saturn, Uranus, and Neptune, and finally, last of all, Pluto, way out at the edge of things. This is the distance relationship, or rather the order of these things. Size is something else again. The sun, of course, is the most tremendous object in the solar system. It has far more than 99% of all the material, all the mass of the solar system. Here is a diagram which shows this size relationship. Here's just a segment of the sun, just a little piece of it, you see. And on the same size scale, here are the planets. Here are the small ones, Mercury, Venus, the Earth, and Mars, and little Pluto way up at the other end. Then come the big planets, Jupiter, Saturn, Uranus, and Neptune. Now, there is, of course, a very obvious size division in this arrangement. And we're going to take advantage of that, and this morning we are going to talk about the small planets of the solar system. The smallest of all of these planets, and the first one out from the sun, is Mercury. Mercury is a little fellow, 3,100 miles in diameter, less than half of the diameter of the Earth. And Mercury moves about the sun at a mean distance of 36 million miles from the sun. Now, this term mean distance is made necessary by the fact that the orbits, the paths that the planets take as they go about the sun are not circles but ellipses. This is an ellipse. So that at one time in its journey about the sun, a planet, Mercury or any of the others, is much nearer to the sun than it is at another time. When Mercury is at the point in its orbit which brings it nearest to the sun, that point, incidentally, is called perihelion. It comes from 2 Greek words, peri meaning near to, and helios, the sun. Mercury is 28.5 million miles from the sun. Now, when Mercury, in its journey around the sun, reaches the opposite point in its orbit, where it is most distant from the sun, and that's aphelion, again from a couple of Greek words, apo meaning far from, and helios, the sun, it's 48.5 million miles from the sun. And the mean distance between these two extremes is 36 million miles. And that mean distance, incidentally, is the one always used in talking about the distance of Mercury or any of the other planets from the sun. Now, Mercury moves in this path about the sun at a speed of about 30 miles a second to make its journey about the sun in 88 of our days. That's Mercury's year. Now, notice this. As we talk about these planets in the solar system, those which are nearer to the sun are moving much faster than those which are farther away. Mercury is at 30 miles a second. Now, we can illustrate this. It's a principle of angular momentum. We have a governor here, simply 2 rather heavy spheres mounted on a couple of arms, and this governor is used to regulate the speed of machinery. We start it moving rather slowly. Now, without giving it another push, we just bring those 2 spheres closer together and see what happens. They immediately speed up, and we separate them, and they slow down. That illustrates the principle upon which the planets move about the sun. The nearer planets go faster, and those more distant go slower. Now, Mercury is much closer to the sun, of course, than we are, 36 million miles. That means that the angle between the sun and Mercury, as we see it, is rather small. And we can never see Mercury for, more than an hour at the most, either before sunrise in the east or after sunset in the west. It's very close to the sun. Now, twilight in this part of the world lasts about an hour and a half. So, you see, we never see Mercury in complete darkness. It's a very difficult thing to see. Mercury's rapid motion about the sun is translated, as we see it, by a series of swings, first to one side of the sun and then the other, so that we see Mercury at intervals and then it's hidden behind the sun and we don't see it at all. Now, here is a photograph of Mercury, a picture taken through one of the big telescopes. And you can see that Mercury is not very photogenic. We see Mercury in a phase formation here, in what is called a gibbous phase. That is something like the moon when it's a little bit more than quarter and less than full. That is because Mercury, of course, is nearer to the sun than we are. Its outline is rather hazy and vague. Well, that is the fault of the Earth's atmosphere. Because Mercury is always so close to the horizon as we see it, we have to look at Mercury through a vast length of the densest part of the Earth's atmosphere and do not see it very well. Now, Mercury's closeness to the sun and the sun's tremendous gravitational power have slowed down Mercury's ability to rotate upon its axis to such an extent that Mercury can make one spin upon its axis in the same length of time that it makes one revolution about the sun. This results in the strange condition that the same side of Mercury is always facing the sun. One side of Mercury is in eternal blinding daylight, the other side in bitter night. And Mercury is too close to the sun for comfort. For the temperature on that hot side of Mercury is about 750 degrees Fahrenheit. That's the mean temperature there. Now, think what that means. Next time you have a roast in your oven, open the door and feel the blast of heat that comes out at you. Most domestic ovens have a top temperature range of about 500 degrees Fahrenheit. Mercury's surface is half again as hot as that, the part that's under the sun. The dark side of Mercury, which as far as we know has never seen the sun, is just about as cold as anything can get, pretty nearly absolute zero. The temperature on the dark side of Mercury must be about 450 degrees Fahrenheit below zero. Mercury is at once the hottest and the coldest planet in the solar system. Now, Mercury's mass, that is the amount of material in it, is rather small. And since its surface gravity depends largely upon its mass, Mercury's surface gravity is only about half that of the Earth. In other words, a normal 150-pound man, if he could stand it on Mercury, would only weigh about 75 pounds. This surface gravity, too, is what holds an atmosphere upon the planet. And Mercury's surface gravity is not strong enough to hold any atmosphere there. So there is nothing up there to mitigate these terrible extremes of heat and cold. Mercury is a dead and dreadful world. Beyond Mercury, the next planet out is Venus. And here is a photograph, Venus, showing it in 5 different positions. Now, remember this, that this whole photograph, all these positions of Venus are on exactly the same size scale. And just what that means, we'll cover in a minute. Venus is almost a twin to the Earth in size. It's 7,700 miles in diameter. It goes about the sun in 225 of our days. That's Venus year. And Venus has sufficient surface gravity to hold an atmosphere upon its surface, a very dense, white atmosphere, an atmosphere which reflects sunlight beautifully, so much so that Venus can be very easily seen. Now, Venus, of course, is nearer to the sun than we are, and again, like Mercury, its motions are translated into wide swings to one side or the other, but they're a lot wider than the swings Mercury makes. And we can see Venus at times for as long as 4 hours before sunrise or 4 hours after sunset in the sky. And when Venus is most favorably situated, its nearness to us, it can be only 26 million miles from the Earth, and combined with its white reflective atmosphere, make it the 3rd brightest object in the sky. Now, let's see what happens as we watch Venus when it's going about the sun. As we see it from the Earth, Venus, of course, is at times directly beyond the sun from the Earth. Sometimes we can't see Venus at all. It's hidden behind the sun. At other times, because Venus' orbit is a little bit angled, we do see Venus above the sun or below it, and at such times we see it in its full phase. We see its completely lighted side. Now, as Venus goes around the sun, we can begin to see it, Venus itself, out beyond the sun. Then it is in what we call a gibbous phase, as we saw Mercury. A little further around, it would be in its quarter phase. Still further, it would reach the point where the angle between Venus and the sun as we see it is largest, and we'd see it as a rather stout crescent. And just beyond that, when the crescent is very thin, but nevertheless when Venus is near to us, is when it's brightest. Now, when we saw Venus full, it was 160 million miles away. When we're seeing it now, although we see very little of its lighted side, it's only 40 million miles away, and perspective makes it very, very bright. The atmosphere of Venus, this white atmosphere, is composed largely of carbon dioxide. We've never been able to find any oxygen or water vapor up there. Now, carbon dioxide is a very handy chemical. In solid form, it's dry ice. As a gas, it's a wonderful fire extinguisher, and it's the bubbles in our soft drinks, but we can't see through it. Now, the appearance of Venus, if we could get close enough to see it, might be very much like this, a dense, white, impenetrable cloud. But below that covering of carbon dioxide, almost anything can happen. You see, we've never seen the surface of Venus itself. We don't know what it's like. And there are two pretty wide opinions about what the possibility there. One of them is that Venus is a swamp, a very watery, terrestrial, a celestial rather, hothouse with a very lush growth of vegetation. The other one is almost diametrically opposed to that. They say that Venus is a completely waterless desert like this. Well, who knows? You pays your money and you takes your choice. The third planet out from the sun is the one we live on, the Earth. We are number 3. And because the Earth is rather important to us, it will have a program all of its own. Beyond the Earth, its nearest neighbor outside of the Earth from the sun is Mars. And Mars is, in many respects, the most interesting of the planets. Now, Mars is small. It is 4,120 miles in diameter, a little more than half the size of the Earth. It is at a mean distance from the sun of 141 million miles, and it goes around the sun in 687 of our days. That's Mars' year. Now, Mars travels at about 15 miles a second. See, the slower planet, Mercury 30, Venus 22, the Earth 18.5, Mars 15 miles a second. The angular momentum idea. Mars also rotates upon its axis in almost the same time that the Earth does. Mars' day is 24 hours and 37 minutes long. Now, Mars' orbit is quite eccentric. It's very elliptical. And the Earth goes around the sun inside the orbit of Mars and much faster, so that the Earth overtakes and passes Mars every 2 years and 2 months. Now, when these chance meetings take place, if they happen, when Mars is nearer the sun at this perihelion point, it is also very near the Earth. And it is at such meetings that we can see Mars best, but they don't happen very often, about once every 15 or 17 years. And what we have learned about Mars has come to us in little bits and pieces accumulated at these fortuitous times through the years. If you look at Mars through a telescope, one of the telescopes best adapted for planetary work, it's still hard to see. You see a little pinkish ball, and it's bubbling, it's boiling. Now, that boiling is our atmosphere, is turbulence in our atmosphere. Occasionally, however, if you're patient, that'll clear up, and Mars can be clearly seen. Now, when Mars is seen, it has very definite surface characteristics. There are 3 colors which distinguish Mars. One is a sort of a background of brickish red. Then there are several irregularly shaped green areas and a rather dazzlingly white cap at the pole of Mars. You see, Mars has seasons, just very much as the Earth does, and for the same reason. Mars is tipped away from the vertical on its axis. And when it's winter at one end of Mars, it's summer at the other. And on the winter end of Mars, this cap gets quite large. Now, that is probably frozen water. I hesitate to call it ice, because there isn't enough body to the Martian atmosphere to produce ice. It's frost, frozen water, because it melts, it shrinks as the seasons change on Mars. And as it shrinks, its outline is marked by a rather broad brownish band, such as water might make soaking into sandy soil. There are other seasonal changes on Mars, too, which are extremely interesting. This greenish region here changes with the Martian seasons. In the Martian spring, it's a very pale, delicate green. In the summer, it ripens to a rich, almost bluish green. In the autumn, Martian autumn that is, it's yellow and brown, and in the winter it fades out to a rather lifeless gray. Now, we have that same color change here on the Earth. It's vegetation. And this may be vegetation on Mars, the only evidence we have of any kind of life outside of the Earth. If it is vegetation, it isn't trees or grass. It's a very primitive form of vegetation, moss or lichen, that can stand tremendous changes of temperature and so on. Now, the reddish area is mostly desert. About 70 years ago, a great Italian astronomer, G.V. Schiaparelli, spent a wonderful summer observing Mars. He had one of these favorable positions of Mars. He had beautiful weather. He had a wonderful telescope. And he wrote a voluminous report on what he saw. And he was able to see a number of things that nobody had seen before. Now, Schiaparelli in his report said he's going to try to identify the features he saw on the surface of Mars by comparing them to similar features on the Earth. There were capes and promontories and mountains and channels and so on. And Schiaparelli saw on the surface of Mars a network of fine lines crisscrossing almost the whole of the surface. He called these channels, and the word he used for channels was canali. Well, canali looks and sounds very much like the English word canal. And that's the way it came out when Schiaparelli's report was translated. And the fat has been in the fire ever since. Now, about half of the professional astronomers who devote their whole careers to the observing of Mars have seen these canals. The other half have not. And here is an artist's conception of what these canals might look like. Now, you can see that they are not regular and even like engineered jobs. They're natural channels, if they exist at all. We just don't know. They have never been successfully photographed. Pictures of Mars, and there have been many of them taken through the great cameras, just don't show the photographs. Now here we can see two very excellent pictures of Mars. They show the polar cap, they show the red areas and the green regions, but no canals. That may be the fault of the camera. The grain of a photographic emulsion is much coarser than these canal lines would be in the picture, and therefore they don't come out. In any event, to be seen at all from a planet at Mars distance, the canals would have to be 20 miles wide. And what on Earth, or what on Mars, anybody want with a 20-mile wide canal, we just don't know. The canals are still a moot point. We just don't know whether they're there or not. And the only way in which we will find out, probably, is when the first rocket ship gets up there, the intrepid crew will get out and they will either walk right over where a canal ought to be or fall into one. Mars has two very interesting little satellites, the most peculiar satellites of any planet. They were discovered in 1877 by an American astronomer named Asaph Hall. They are very small. The biggest one is 10 miles in diameter and the smallest about 5. The larger one, the outer one, named Deimos, goes around Mars in about 30 hours, in just a little more than one Martian day. But the inner one, Phobos, about 4,000 miles from Mars, whips around Mars 3 times a day. Now, like any well-educated satellite, it goes through all the phases of a moon each time it goes around, so that theoretically Mars could have 3 full moons a night. Well, astronomy hasn't figured out yet a practical use that you can make for 3 full moons a night. It might serve to speed up Martian romance a little bit, but there is a practical use for these things, really, in the future. They are built-in space satellites and will be used, I'm sure, in time for the observation of Mars. The last of the small planets, the most distant one in the solar system, is Pluto. And here is a photograph of Pluto. Pluto is so far away and so faint that we have to identify it in this picture by pointing an arrow to it. Now, Pluto was discovered mathematically before its presence was ever actually known. Neptune is the next planet nearer the Sun than Pluto. And Neptune had been going along its orbit for about 50 years after its discovery in 1846, before it was noticed that Neptune was not following its expected path. It wasn't going straight. It was, there were variations in its path. Now, these variations are called perturbations in the orbit of a planet. And they are evidence that there is some other body out there disturbing the normal course of a planet about the Sun. One of the great American astronomers, Percival Lowell, set himself the task of finding out whatever it was that was bothering Neptune and making it wander through space. He called it Planet X, and he started in by calculating its possible position mathematically, which was considerable of a job. Then Lowell died in 1905, and the task was taken over by a young American astronomer named Clyde Tombaugh, who took literally thousands of pictures of the region in which this planet was supposed to exist. Now, here are a couple of pictures of Pluto, taken in that same way. Here again is Pluto. It must be identified by an arrow. Notice its position in relation to the stars, one on either side of it. Now, the next night, another picture of Pluto was taken. Same arrow, same Pluto, same stars, but notice the change. That is what gave Pluto away, its motion among the stars. Pluto was discovered in February of 1930. Its discovery was not announced until March, however, on March 14th, which was Percival Lowell's birthday. Then it made the headlines. Here is a copy of the New York Times for March 14th, 1930, and up here in a prominent position is the headline announcing the discovery of Pluto. 9th planet discovered, on edge of solar system, first found in 84 years. That's Pluto. Out there, 3.5 billion miles from the sun, taking 248 of our years to make its weary journey around the sun. Now, Pluto, that 3.5 billion miles, incidentally, is, again, its mean distance. It can, at times, be closer to the sun than the planet Neptune. Here, for instance, is the orbit of Neptune. Here is the orbit of Pluto. And you can see that in 1989, Pluto will actually be nearer the sun than Neptune is. The two planets won't collide, however, because Pluto's orbit is tilted away from the horizontal, and the nearest they can possibly come is something more than 200 million miles. We don't know very much about Pluto. It's very faint, very far away, very hard to see. It's probably a little smaller than the Earth, somewhere between the Earth and Mars in size. It has no atmosphere. Its temperature, out there 3.5 billion miles from the sun, must be equally as cold as the dark side of Mercury, just about 450 below zero, almost absolute zero. It has no atmosphere. There are no traces of any satellites. Now, let's see what we have learned about the solar system today. We have it here, this little affair, which again is not a model, remember that. But the 9 planets are there. Now, we have talked about the smaller planets, 4 of them situated very close to the sun. The 5th one, the exception, at a vast distance from the sun. That's Pluto. Now, these 5 small planets all have a sort of a relationship. They're all small, about the same size, nearly the size of the Earth. And for that reason, they're called the terrestrial planets. They also have a very small proportion of the solar system satellites. Mercury has none, Venus has none, the Earth has just 1, our moon, Mars has 2, Pluto has none. They're not too rich in atmosphere either. Mercury doesn't have any atmosphere. Venus, of course, does have a rather thick one. The Earth has an atmosphere, we breathe it. Mars has a very, very thin one, Pluto has none at all. These are the little fellows. Now, we don't know whether there is any other planet out beyond Pluto. If there is, it is so vastly far away, at such a tremendous distance, that its possible discovery will surely be a matter of chance rather than any plan that man may make to find it.
This is National Educational Television.